Hello and welcome back. All right, now, in order to cash in on this, or to cash out, I should say, the details of this new universal theory of gravitation, we said Newton needed to develop a new mathematics, and that mathematics was the calculus. It's a great step forward. It has a lot of calculatory power, but the way he did it with infinitesimals, as I said earlier, is something of a step backwards in the concerns of this sort of video series, understanding what we're doing, understanding philosophy better, or infinity better, and untangling problems with infinity and stuff. It's almost kind of backwards. We're definitely in the era of if it works, it works. And the calculus worked until it didn't. And we'll get to that later too. So we're going to take a look now. Now, I'm going to start by contradicting myself and explaining how the calculus, Newton's infinitesimal calculus, can be used to explain or untangle, if you will, or answer one of those Zeno's paradoxes, the paradox of the arrow. Well, let's take a look, remind ourselves what that was and what Newton has to say about it. So the paradox of the arrow is this. It's founded on the assumption that at any given instant in time, a thing is either moving or stationary, but not both. And we have an archer here with his little bow and arrow, firing an arrow towards a target here, and the arrow's flying across, right? And now the question is, what is the speed of the arrow at this instant in time? Right there. Picture that arrow at that instant in time. It's not covering any distance, so its speed at that instant in time is, of course, 0. And the fact that I put that halfway between doesn't matter. The speed of the arrow at this instant in time, at this instant, would also be 0. The speed at this instant in time would also be 0, and so on. So it seems that at every instant in between the archer and the target, the speed of the arrow is 0, and yet it still seems to move somehow towards the target. This is what Zeno brought up in order to show that Parmenides' assertions that motion and change are all an illusion was actually true, and you can prove it from the Zeno's, or from the Pythagoreans' own assumptions. Okay. This actually is a sort of a magic trick, a sleight of hand. Let me show you where the sleight of hand occurs. When I tell you about thinking about that arrow at a certain instant in time, I am emphasizing the fact that the change in distance it makes, that little triangle there is the Greek letter delta. Mathematicians use it to mean change. The change in distance at that point in time is 0. And therefore I say, therefore its speed must be 0. But that's not quite right. Speed is the change in distance over the change in time. And at that instant of time, the change of time is also 0. My sleight of hand is drawing your attention to the numerator and drawing it away from the denominator. In mathematics, dividing by 0 is bad. 0 over 0 is, at the very best, complicated. So I didn't actually prove that the arrow was stationary at that point in time. However, not proving that the arrow is stationary doesn't exactly prove that it's moving either. So how can we come up with the actual speed of the arrow at that instant in time? So let me start talking about it. We can imagine doing this to try to figure out. Imagine taking a camera and videotaping the arrow as it moves across. Now, we can take 2 adjacent frames in that recording and then see how far did the arrow move between each frame and divide it by that very, very, very small amount of time that passes between frames. And that will get us something very close to the arrow's exact speed at that exact point. So very close, but not exactly. How can we get its exact velocity at that point in time? Newton's answer is, let's let that time interval that passes between the first frame and the second frame, let's let that time interval be infinitely small, infinitesimal. Then if we let it be infinitesimal, but not 0, we'll get the exact speed of the arrow at that time. Now, if you've never had calculus, or if you have, and that doesn't quite make sense to you, you're not missing anything. It doesn't. But what you can do with it is you can calculate with it, and you can get mathematical answers. Let's take a look at how we can take this idea and get actual mathematical answers out of it. All right, back to the whiteboard. So let's say we drop a rock. And let's say the rock, after t seconds, falls t squared feet. Yes, yes, I know it should be 32t squared, but this is just for simplicity's sake. That's not the point of this whole thing. All right, so that means at 1 second, it's at 1 squared or 1 foot of dropping distance. Now, let's proceed an infinitesimal small amount after that 1 second. We're going to use the letter h to represent our infinitesimal at 1 plus h second. At 1 plus h second, its actual drop distance is 1 plus h squared. Now, when you square something, that means you multiply it by itself, and now we FOIL firsts, outers, inners, lasts. And so that gets that at 1 plus h seconds, the rock has fallen 1 plus 2h plus h squared feet. All right, and that whole duration of time was h, an infinitesimal amount of time. So the speed, which is the change in distance over the change in time, is going to be our ending distance, 1 plus 2h plus h squared, minus our starting distance for that interval, 1 squared, over the amount of time that passed, h, the infinitesimal amount of time. Now here's the thing. If that h were 0, and we plug that in, we would get 1 plus 0 minus 1 squared minus 1 squared over 0, which is going to be 1 minus 1 over 0, or 0 over 0. So if h is 0, that gets us back to this situation that we were looking at in the paradox of the arrow. That's bad. But let's do a little algebra first. Notice that this whole numerator becomes 1 plus 2h plus h squared minus 1 over h. And the 1's cancel. Now, we have an h common to both of our remaining terms, and we can factor it out like that. 2h plus h squared becomes 2 plus h times h. I factored out the h. And that factored out h now cancels with the h in the denominator. So after a little algebra, we get that at 1 second, if we look at the distance between, or the difference between 1 second and 1 plus an infinitesimal amount later, we get an instantaneous velocity of 2 plus whatever that infinitesimal amount is. And so now if we say, well, that amount is infinitesimally small, so we can neglect it, now we get an answer of 2 feet per second. So we have just concluded that the arrow is traveling, or the rock, the falling rock at 1 second is traveling at a speed of 2 feet per second. Ta-da! And there we get it. We can actually get, through this use of infinitesimals, a speed at that instant in time. Whew. Now, let's see, what do we got here? So this is the math that Newton used in order to cash out his whole theory, universal theory of gravitation mathematically, and it all worked. Now, if we want to understand what's going on, our solution does have some problems. Is h 0 or isn't it? Newton would say, no, it's just infinitesimally small. Well, if we have all these problems with the infinitely big, I don't see how introducing a new infinity, the infinitely small, is going to help out at all. It creates more questions than it answers as far as understanding things are going on. But recall the change in opinion of what science is about that Newton sort of ushered in. Newton said that science is not about explaining what you're seeing, but about describing what you're seeing mathematically in a way that can allow you to make predictions, testable predictions that could be accurate or not. So for example, he never explained gravity, but he came up with the mathematical theory of it, which allowed him to, so for example, predict where planets would be at a certain point in time. And it worked. And similarly, he isn't really interested in explaining infinitesimals or understanding them, just creating them. If they created a system you can calculate with to make predictions that were accurate, that's really all he cared about. We're definitely now solidly in an era of if it works, it works. And so that's where Newton and the scientists around him came from. Now, some people did, of course, bring up objections about these infinitesimals. They don't make any sense. But as you can imagine, then, just as now, by and large, mathematicians and scientists didn't really care about what philosophers had to say. as long as it worked, which is going to be a crucial thing. Let's talk about one of these critiques was by a philosopher named Bishop Berkeley. Wait, let's back up. Let me talk a little bit about social context. Now, although Newton and his fellow scientists or humanists or whatever were really interested in operating outside of the authority of the church, sort of a free-thinking way, they were still pretty much by and large Christians. However, remember back with the scholastics, although they believed God could do miracles, they believed he did not do them very often. And so therefore, if you're going to have an adequate explanation of like why it rained, you really can't invoke just God's will in it. There should be a better, more rational, more scientific explanation of why it usually rained as opposed to miracles. And that kind of emphasized more and more. With Newton's system of universal theory of gravity and explaining all this new physics and stuff, that was pushed more. Scientists seem to be able to explain more and more without having to invoke a divine creator. A French mathematician by the name of Laplace eventually developed out the system of the whole solar system, the mathematical theory of the whole solar system. And when he brought it to his emperor at the time, Napoleon said, well, where is God in your theory? To which Laplace replied, I have no use for that hypothesis. So he wasn't quite denying that God existed as much as he was saying that he didn't really need to invoke God in his whole explanation. However, through the years, this did develop into a strand of rationalistic atheism and the belief in that the materialistic universe and that everything can be explained without appeal to God. And so therefore, there really is no reason to believe in a God. Berkeley, in an essay he wrote called The Analyst, was criticizing that stance. Calculus was called analysis, and so an analyst is someone who does calculus. And Berkeley criticized analysts who balked at believing in a divine creator, and yet still seem to believe in these ghosts of departed quantities. As I said earlier, at the time, no one really paid attention to him until later. Once things started going badly, and that's a future lecture, then they started looking back, and that's why we know about this now. But we will get to that, like I said, in a future lecture. Before we get to that, however, we do need to cover one topic that is crucial for understanding everything that came after it. If we want to really understand what people thought about what they were doing and what it meant and things like that, we're going to need to understand the philosopher Kant. Kant has been said to have created a whole Copernican revolution in philosophy and how people thought about what they were doing. That really did influence everything that came after that. And all of the rest of the philosophy and the mathematics and what mathematicians thought about what they're doing is informed by what Kant said. So in my next video, I'm going to attempt to explain Kant well enough so that you can follow the subsequent videos. As you could tell by my reaction, perhaps, that will be a bit of a challenge. But at least it's not Hegel. And after that, I'll just give a quick summary of what's going on for the rest of these videos. After that, we're going to follow two strands. First of all, we're going to pick up again on these problems with the parallel postulate, Euclid's fifth axiom, and how people struggled with that, and then the development of non-Euclidean geometry. And on the other hand, we're going to follow the story I've been teasing all along of the collapse of the calculus, the development of the theory of limits in order to approach that. And the thoughts and ideas and perceptions that come out of these two strands are going to come emerge in the development of transfinite arithmetic, of new foundations of mathematics, and a new perspective of what mathematicians even think about what they're doing and what mathematics is. It's going to be a whole scientific revolution in mathematics about what they think they're doing. In case you have experience with some mathematics and are familiar with the mathematics, just a little quick teaser. So this is kind of what I'm getting at. The Euclidean axioms were axioms because they were believed to be just so obviously true. Between any 2 points, you can connect them with a line. Group axioms, on the other hand, serve as a definition of what a group is. How exactly did we transition from thinking our mathematicians are about things to just about the consequences of definitions we've come up with? So that is perhaps like the explanation of that, the explanation of what it is I just said, how it happened, why it happened, what people thought about it as it was happening is sort of the climax of this whole video series. And that's what these two strands of non-Euclidean geometry and the development of the limit theory of calculus are going to merge into and lead into. And we're going to end off the video series looking at the consequences of that afterwards. All right, well, hopefully that sounds good to you. And I look forward to going through all of that with you in the future. Thanks a lot.